So this is where we're starting. Now, we did finish the last lesson with this one. Well, not so much that one, but this one here for sure. Well, yes, we did do the other one. This one. Now, we noticed the fact that it's not all in terms of cosine, and we had to make it be that way. We had to change sine squared to 1 minus cosine squared. So that way the entire function is in terms of cosine, and we can treat it like a quadratic. Now, luckily for us, the next one was completely in terms of sine, so we didn't have any real issues with this one here. Now, the next one, 3 secant squared minus 2 tangent squared minus 4 is equal to 0. We need to solve for the value of x between 0 and 2 pi. Now, there's different ways we can go about doing this. Well, would have been nice if I still had my here. No, went too far. Pythagorean triple or Pythagorean identities posted here, but that's fine because the Pythagorean identity with this here says that tangent squared of x plus 1 is equal to secant squared of x. So we can do this in one of two ways. We can either replace secant squared with tangent squared plus 1, or we can replace tangent squared with secant squared minus 1. I think it'll be a little bit easier to just replace secant because it's one term. So we'd still have the 3, but instead of secant squared, we have tangent squared of x plus 1. And we get this here. Because whenever we solve, we either need it all in terms of sine, all in terms of cosine, all in terms of tangent, all of the equation in terms of the same trigonometric function. That way we can solve from one to the other. Now for this here, the first thing we need to do after rewriting it all in terms of tangent is distribute the 3. Well, that gives us 3 tangent squared of x plus 3 minus 2 tangent squared of x minus 4 is equal to 0. Now at this point, we're going to combine like terms. 3 tangent squared minus 2 tangent squared as well, tangent squared of x. Plus 3 minus 4 is minus 1 is equal to 0. Well, since we do not have a middle term, we don't have tangent to the first, we can get tangent by itself and then solve from there, because we can add 1 to both sides, telling us that tangent squared of x is equal to 1. Questions on this here? Now, since I got tangent by itself, we can use the square root method. And I can take square root of both sides. And the square root of tangent squared is just going to be tangent of x equals plus or minus. Because whenever we take square root of both sides, we have to add the plus or minus. Incidentally, yep, square root of 1 is 1. And we have this here. Now really we have two statements. We're saying that tangent of x, tangent of whatever this angle is equal to positive 1. And tangent of whatever this angle is also equal to negative 1. Now this will give us 4 possible angles, because with tangent, if we look at the unit circle, tangent is 1, well, we're more looking at the chart, at 45 degrees, or pi over 4. And it's really where sine and cosine have the same value. Now looking at this here, we said it is, indeed, pi over 4 when x is 1. But it's also positive 1 when both sine and cosine are negative, which is pi over 4. Now, when sine and cosine signs are opposite, we do get negative 1. at our pi over 4 angles as we go around the unit circle. So that's telling us this other one is 3 pi over 4 and 7 pi over 4. And these here are our 4 solutions. So really, when we're doing this tangent equals 1, tangent equals -1 on the unit circle, we're going around and seeing where that is true. Now, tangent of x equals 1 at pi over 4 or 45 degrees. So we're looking at kind of the 3 other reference angles of 45 or pi over 4, which is our 3 pi over 4, 5 pi over 4, 7 pi over 4. And since, well, we have it as positive and -1, we want all of them. Questions on this here? There we go. Questions on any of this? So we're good so far. All right. Let's look at the next one. This one here. We want to solve cosine of x plus 1 is equal to sine of x. We get this here. Cosine of x plus 1 equals sine of x. Well, as I said already today, we need these equations either all in terms of cosine or all in terms of sine. We can't have it as one or the other. So we need to do something about that. And the only way that we can replace sine with cosine or cosine with sine is if we have sine squared or cosine squared. So let's actually make that happen. And to make that happen, we're going to square both sides. We're going to square both sides so that we do get the sine and cosine squared. Now on the right-hand side, sine squared is, well, just sine squared of x. And that's it. Because sine squared, sine times sine, sine squared. On the left-hand side, we really have cosine of x plus 1 times cosine of x plus 1. We have to be multiplied by itself. Because of that plus in the middle, I can't just square both terms and be done. I have to actually multiply it out. So we're going to have cosine times cosine, which would indeed be cosine squared of x. And we have cosine times 1, which is just cosine of x. 1 times cosine of x would be plus cosine of x, and 1 times 1 would be plus 1. So we do need to do some simplifying on the left-hand side. Now, again, we need to get it all in terms of sine, all in terms of cosine. So there's 2 directions we can go. One is turning cosine squared into sine squared. The other is turning sine squared into cosine squared. Now, turning cosine squared into sine squared would get us nowhere because of our 2 cosine. If I did that, I would have 2 things in terms of sine, 1 in terms of cosine, and it really didn't help us get everything in terms of the same one. So here, what we're going to have to do is turn our sine squared of x into 1 minus cosine squared of x. I know there's not a whole lot of room on that reference page, but I would definitely fill in our other forms of the Pythagorean identities. So the fact that sine squared plus cosine squared equals 1 is also sine squared equals 1 minus cosine. Cosine squared is equal to 1 minus sine squared, so that you have those as a quick reference, so that you're not having to solve or try to solve it in your head every single time you're working these. Does that make sense? Same with tangent cotangent. Now again, for most all of these here, since we are dealing with another quadratic, we have a squared term, we'll want to get this equal to 0. So we can add cosine squared of x to both sides, which will give us 2 cosine squared of x plus 2 cosine of x plus 1 is equal to 1. Then again, to finally get it equal to 0, we're going to subtract 1 from both sides. Any questions on how we got down to 2 cosine squared of x plus 2 cosine of x equals 0? Well, now we need to solve. We can solve by factoring. Technically, we can solve by the quadratic formula. There's different ways we can go about solving. I would go by factoring because we don't have a constant term. And the first thing we do in factoring is find a greatest common factor between these two. Well, I don't write over the top of it. 2 is in common with both terms. Is there anything else? Yeah, cosine. Yeah, 2 cosine of x is in common with both, because if we take 2 cosine of x out of 2 cosine squared, we just have 2 cosine of x plus 2 cosine factored out of 2 cosine would be 1. Questions on how we got to this point? Now, according to the zero product property, if we have 2 or more things multiplied together to equal 0, one of them must be 0. Now, one of them is cosine of x plus 1 is equal to 0, yes? What would the other one be? Cosine of x, yes? Now, it's very tempting, and most would say that it's 2 cosine of x equals 0, and cosine of x plus 1 is 0, and there's nothing wrong with that. But again, what did we say? Zero product property. 2 or more things multiplied together to equal 0. One of them must be 0, yes? And we normally think of it as 2 cosine of x and cosine of x plus 1. What is the 2 and cosine of x? What is the operation between them? Well, the operation between these two is multiplication, yes? So what's actually being multiplied here? 2 cosine of x and the quantity cosine of x plus 1. So we actually have 3 things, yes? Is there any way I can turn the number 2 into 0 just by the number itself? Well, no, it's just a number. So we're not really focused on this 2 because I can only really turn cosine of x into 0. That 2 is gone. You're good. You can leave it there. Because even if we did have it, and you don't have to write this in, if we said 2 cosine of x, well, the first thing I would do is divide both sides by 2, which would indeed give me cosine of x. And 0 divided by 2 is still, so we can just say cosine of x. Now, cosine of x equals 0, especially on the interval 0 to pi, it's kind of nice to find. Because I can grab the unit circle. Cosine is the x value in the ordered pairs on the unit circle. So I find where it is at 0 and is at pi over 2. And incidentally, with 0, we do have 2 of them, and that is at 3 pi over 2. Sine and cosine only equal 1 or negative 1 once, respectively, between 0 and 2 pi. It does equal 0 twice, mainly because 0 is not positive or negative, so it shows up twice. Now for our other one, to solve this here, we do need to subtract 1 from both sides, telling us cosine of x is equal to -1. Yes? Couldn't tell if you had a question or had to sneeze. And if we look at the unit circle, cosine of x equals -1 at pi. Questions on this here? Now these we have to check. These answers we have to check them to make sure they work. Now up to this point we really haven't had to check any of our answers. Pi over 2, 3 over, yeah. So pi, 3 pi over 2, and pi over 2. These are the three answers we got. We need to check these, and there's a reason for it. Because our first step in solving was to square it, yes? The issue with squaring is if a number was negative and we square it, it becomes positive. If a number was going to be originally positive and we square it, it stays positive. So if one of these two sides did indeed have, say, cosine of x plus 1 worked out to be 2, well, that actually wouldn't be 2, worked out to be 0.5, but sine of that same angle worked out to be -0.5, and our first step in this process was squaring it, we have 0.5 squared, and our -0.5 squared is now going to become the same as positive 0.5 squared. We have an issue because of the signs. So we have to check these, if that makes sense. And it'll make more sense, especially when we look at this here. Because if we check cosine of pi over 2 plus 1 is equal to sine of pi over 2, we could plug this all into the calculator, or we can use the unit circle. Because cosine of pi over 2 is 0. So we have 0 plus 1. Sine of pi over 2 is 1. Well, 0 plus 1 is 1. 1 does equal 1, and we're done. One other thing, as a side note, whenever we check, we can't add or subtract things across the equal sign. We just do both sides and make sure they're the same. That's fine. Let's check pi. Cosine of pi plus 1 is equal to sine of pi. Well, cosine of pi is -1. So we have -1 plus 1 is equal to sine of pi, which is 0, and -1 plus 1 is 0, equals 0. Well, it's not looking like a whole lot of reason we had to check these, yes? Let's go on and just check the last one for the heck of it. Oh, I'm going to flip it apparently. Sine of 3 pi over 2 is equal to cosine of 3 pi over 2 plus 1. Well, sine of 3 pi over 2 going straight down is -1. Cosine of 3 pi over 2 is 0 plus 1. -1 is equal to 1. Yes? No. Three pi over 2 doesn't work. Now, the reason we got it as an answer is because if we think of these in terms of their value, well, again, the first thing we did was square both sides. Well, our -1 squared would have been 1. 1 squared is 1, so 1 does equal 1. That's the issue when we square both sides. We get extraneous solutions because of that sign change that occurs due to squaring. Now, could we solved it by hand without it? Well, no. We needed that to solve it, but we do get extras that we don't need. Questions on this here? It might be good to do another, yes? When we don't have a square in sight and we have sine and cosine or or tangent, secant, cosecant, cotangent, those Pythagoreans, we're going to have to square both sides. Now on the right-hand side, well, left-hand side, we're really saying we have sine of x plus 1 times sine of x plus 1 is equal to, well, cosine squared of x. Now when we distribute this out, sine of x times sine of x is sine squared of x. We have plus sine of x, because our sine of x times 1. 1 times sine of x would be plus sine of x, and 1 times 1 is 1. And what this gives us is sine squared of x plus 2 sine of x plus 1. I think we feel pretty comfortable with multiplying that out, yes? Now the right-hand side, cosine squared of x is equal to 1 minus sine squared of x. And again, just like the previous problem, we need to get this equal to 0. So, first thing we can do is add sine squared of x to both sides, which will tell us that we have 2 sine squared of x plus 2 sine of x plus 1 is equal to 1. At this point here, we can subtract 1 from both sides, telling us that we have 2 sine squared of x plus 2 sine of x is equal to 0. Greatest common factor is sine of x. Which does leave us with this here. Now we do need we have 2 things multiplied together to equal 0. One of them is sine of x, and the other is sine of x plus 1. Now sine of x equals 0 at 2 points. One of them is incidentally at 0. Degrees or radians, really, that's going to be the same value. The only angle, funny enough, and pi. The other one we do need to solve. We need to get sine of x first to be able to find the angle. And sine of x equals -1, going straight down at 3 pi over 2. So again, we have 3 values, and we need to check them. Now, we can do this in a calculator. We did the last one by hand. We can do this in a calculator. Now, the problem they gave us was sine of x plus 1, so sine. Oh, delete that whole thing. Because our first angle was 0 plus 1 gives us 1 is equal to cosine of 0 is 1. So they equal the same value. So we're good there. So for our solutions, x does indeed equal to 0. The next one we can try is pi. Sine of pi plus 1 is 1. Cosine of pi is also 1. Yes. No, it is -1. So what that tells us is that x cannot equal pi. And the last one was 3 pi over 2. Sine of 3 pi over 2 plus 1 is 0. Cosine of 3 pi over 2 is also 0. Let me get this here. Now it is interesting, I do not know for certain if this is a solid fact, but a lot of our issues are coming from when sine of x is equal to 0, or cosine of x is equal to 0. One or the other kind of gave us those offsets. Yes? Any questions on any of this here? There we go. Are you ready for the next one? 2 cosine of 3t. I don't like that the book does this, but a lot of books actually do this. If there's no parentheses around whatever's after cosine, sine, tangent, secant, cosecant, cotangent, it's assumed that we understand that the 3t is inside of cosine and the -1 is not. Because if the -1 was a part of the 3t inside of cosine, they would have put parentheses around it. I don't like that because it's all based off assumptions that we should know it. I feel like we should put them there anyways. But that's not a hill I'm going to die on today. Hopefully not ever, because that's minute details. But it seems like this should be different than what we've done so far because the angle is 3t, not just t. However, we can solve it the same way. We don't have double angles, half angles to worry about because if we get it by itself, first thing we do is add 1 to both sides. We get that 2 cosine of 3t is equal to 1, which honestly is neither here nor there because we don't have it by itself yet. But the next thing we need to do to get cosine by itself is divide both sides by 2, telling us that cosine of 3t is equal to 1/2. Now, this is part of the reason we don't have to use half angle, double angle formulas is because 1/2, is it on the unit circle? Well, yeah, it's one of our nice values. And if we looked at this here, cosine of our angle, so 3t, for whatever value t, gives us cosine value of 1/2 at pi over 3 and 5 pi over 3. Because it gave us nice values, the angle gave us some nice values of 1/2, gave us the nice value of 1/2, we can go on and just use this here. We don't have to use the half angle, double angle, triple angle. We can go on and do this here. Now, because they didn't restrict it to being between 0 and 2 pi, we do have to add one thing to it. Pi in, because it could be any angle going around the circle. So it could be 5 pi over 3 or any iteration of adding or subtracting 2 pi from it. Now it seems like this should be it. We're done. But is the value of t by itself? No. So we have to divide it by 3. Now this is also why we try to, especially when solving multi-step equations, get the variable by itself first before we multiply or divide, because when we do the multiplication or division step, we have to apply it to every part of the equation on both sides. And on the other side, we can do this in one of two ways. One, I can say I'm dividing pi over 3 plus 2 pi n by 3, or I can write it in a more simplistic way, saying the same thing, is that we're dividing both terms by 3. It's the same thing. Personally, I feel this is a little bit easier to work with because 3t divided by 3 is just t. Pi over 3 divided by 3. Well, we could do this by hand. Or I can let the calculator say pi over 3 divided by 3 is pi over 9. Let the calculator do it for us. Does 2 divide by 3 for 2 pi n? No. So it's plus 2 pi n over 3. That's one of our answers. Well, we can do the same thing to the other side. 3t divided by 3 is t. 5 pi over 3 divided by 3 is 5 pi over 9. Plus 2 pi n over 3. So those are our technically two answers. Technically, it's a lot more because n can be any integer. But that's it. Questions on this here? Now these are kind of nice, especially if our angle was restricted, our value of t was restricted between 0 and 2 pi. Well, I think so. I'd have to look back, but yeah, we don't really need the 2 pi n, or shouldn't need it, because there's only 2 spots that it can work. So these are it. Questions on this here? Would you like to look at another? Yes. They're a little bit weird. Because again, with this here, the first thing we're going to do is get sine of 2t by itself. So we're going to add the square root of 3 to both sides, which will tell us that 2 sine of 2t is equal to square root of 3. At this point here, we're going to divide both sides by 2, telling us sine of 2t is equal to square root of 3 over 2. Now, sine does equal the square root of 3 over 2 at 2 places. One of them is telling us that 2t is equal to pi over 3. And the other is telling us that 2t is equal to 2 pi over 3. Now again, because we are not restricted on the interval of 0 to 2 pi, we have to add the 2 pi n into it. Now I will tell you, especially for the test, I'm going to restrict pretty much all of these to be between 0 and 2 pi, so we're not having to worry about this here. Yes. We don't have to worry about having the extra part. Now, the last step would be to divide this one here, everything by 2. Well, our 2t divided by 2 is just going to become t is equal to, we can plug it into the calculator. Pi over 3 divided by 2 would be pi over 6. plus, well, 2 pi n divided by 2 is pi n. We do the exact same thing to the other equation. Divide everything by 2, or 2t divided by 2 is t. Incidentally, our 2 pi over 3 divided by 2 turns into pi over 3 plus pi n. Now, if we weren't restricted, I just realized, if we weren't restricted on being on the interval of 0 to 2 pi, we have to do this here. If we were, we would actually have to plug in values of n, so starting at 0, 1, 2, 3, do the same thing. And whenever that value of n gave us a value for an angle that was outside of 0 to 2 pi, then we had them all. So we had to do the same thing, actually. And the only reason I noticed that was actually from this problem here, because if I plug 0 in, we do indeed get pi over 6. If I plug 1, pi over 6 plus pi times 1 for n, we get 7 pi over 6. Well, that's still on the interval of 0 to 2 pi, yes? It's still a value that works. If I came back over here and replaced 1 with 2, 13 pi over 6 is now outside of it. We have the same thing with pi over 3 plus pi n, 4 pi over 3. So for the other one, t would indeed equal pi over 3 when n is 0. But then we also have 4 pi over 3. And if we did it one more time with 2 instead of 1, we get 7 pi over 3, which is now outside. So we get this here. So for this one, we would actually have to plug in values of n if we're still between 0 and 2 pi. We still have to use it even though it is restricted, because there are a few more angles that have to be taken into account. So that kind of makes sense. It's a little weird until you've kind of done it a few times. Questions on any of this here? Well, I was wrong, because we are, I believe, out of time. Yes. So we're gonna